I'm just adding board. So this is where we get our 171. Okay, 73.171. So I label this and it's megapascal. This will be in millimeters. Okay, and then this will be at minus 25. So over here, you just label this. This is your 73.171, and this is your minus 25. Okay, so from here, you can immediately draw a straight line. You'll be asked to draw this. Okay, I'm very sure of it. Okay, just a very good hint. Okay, there you go. And then after that, you draw your arrows. Okay, so compression pushing towards the what? Pushing towards the axis or the member. And the other side is under tensile, pushing away. Okay. I know this question did not ask for the stress distribution, but I want to teach you how to draw it for the whole example. Okay. So this is the example that we're going to do. Okay, for symmetrical bending. Okay. Any questions so far?
Sir, how would the bending diagram for this one would be?
Bending moment diagram.
Yeah.
Okay, the bending moment diagram. Can I do it in I will post it online. I will post the bending diagram because I have sandwich material to teach. Okay. Hello.
All right. Yeah.
Okay. So after class, I will draw it out and I will show you how the bending moment diagram will look like. Okay.
Yeah.
Right. So the next thing I'm going to draw now is we're going to do sandwich material. Okay. We're going to do sandwich. I hope to squeeze in at least one example for sandwich material. I think it's possible. Okay. So let's deal with sandwich material now. So let's look at sandwich material. This is not a difficult topic at all. Okay, once I explain to you what is going on, okay, and you apply what I teach you, okay. I realize in the term test when I mark, some of you, not all of you, some of you are doing the method based on the solution manual. The solution manual is not done by me, okay. It's done by the publisher, okay. And I will wish some of you apply my method to answer the questions because that will help you in your term test. Why? Because the solution manual method sometimes or most of the time it is very it only works based on the type of question. Like when I give you a question when there is forces and temperature change, when you apply the solution manual method, you get confused. That is why for question number 1, a lot of people make mistake. Okay, I can see it. But those that adopt what I teach and and apply what I teach and not necessarily follow the solution manual methodology of solving, you get it. Okay, and that's why, yeah, the solution manual is sometimes helping and not helping you guys at all. But anyway, so sandwich material, and I hope you all will apply the technique that I'm teaching you. Okay, especially for sandwich material, or not, you can get really confused. So in sandwich material is a structure made of several steel or several material, 2 or more. Okay, if one is not sandwich anymore, right? So we sandwich material. Okay, so sandwich material is also known as composite beam. Okay, so if you look at the term composite beam, it's the same thing. Okay, so the formula changes. Okay, so structure made of composite material or composite beam, the formula changes just by a bit only. Okay, where stress X is equal to, we have an n in a coefficient in front. Okay, multiplied by my over Iyy multiplied by z. Okay, where n is not really n. I don't know what that symbol is called. Okay, it's a Greek, but it looks like n. It's the coefficient okay, it's the coefficient of the reference material. Okay, coefficient of the reference material. So what does this mean? Okay, what does this? All of a sudden we have this. So let's look at a beam now. Okay, a cross sectional view of a beam. Okay, so we have we not a cross section. So we have again we have a beam that is simply supported again. Okay. And then this beam, right, is made of several materials. So you have one material down here, and you have another material down here. Okay. Again, okay. So this is your P in the Y direction. Okay. So this is material one. This is also material one. And this is material number two. Okay. So rather than call it material one, material number two, the top part we call it made of steel. Okay. Steel. And the center one we made of brass. And if we look at here, E of steel, Young's modulus of steel. And I'll tell you why we need the Young's modulus. This is 200 gigapascal. And the Young's modulus of brass, this is at 100 gigapascal. Okay. So case number one, so the formula that we are to find the coefficient, okay, n is equal to E of a material, okay, divided by E of the reference material. And I will elaborate what do we mean by that. Okay. So let's look at the cross-sectional view now. So I'm going to draw the cross-sectional view now. This is Y, Z, rotation by X. So we're going to draw the cross-sectional view now. Okay. So the cross-sectional view, I'm going to change the paper background because it's all relative. So we're going to do this. Okay. So this is our material. Okay. So this is a cross-sectional view. Okay. So this is our steel. steel, and this is our brass. So case number one, let me bring this down lower. So I have a lot of things to write. So case number one, okay, we are going to use steel as reference material. Okay. So when that's the case, the N, okay, the N for steel is equal to E of steel divided by E of steel. Okay. So E, Young's modulus of steel divided by Young's modulus of steel. This is equal to 1. Yes? Okay. However, N of brass now is equal to E of brass divided by E of steel. So this is equal to 100 divided by 200 is equal to half. What does this actually means? Okay, what does this actually means? Okay, you guys see a lot of this, like I believe some of you have done this calculation before. But physically, what it means. So when you say the reference material, steel is the reference material, and let me write this on one line or not, it gets confusing. When you make this statement, steel is the reference material, means how to change this steel. Okay, now everything is made of brass. I repeat again, how to change this structure now that's sandwich. That's now everything is made of steel now. You take out the brass, you put it everything made of steel. But the strength of the structure cannot change. I repeat again, the strength of the structure cannot change. Okay? So sorry, Azam asked, is it okay to write minus 102.439 megapascal? Yes. Okay, megapascal is 10 times 10 to the power 6. That's megapascal. Now coming back to here. So now, how will the structure look like? Okay, how will the structure? Now the structure look like this. If you change everything to steel without changing its strength, okay, it will look like this. Okay, so the top and bottom did not change. So the top and bottom, if you look at the number of squares, is 6 by 1. Okay, so 6 by 1. 2, 4, 6. Okay, it did not change. The top and bottom did not change. Because the reference material is in steel. Now, to change brass to steel, you have to halve its size. Okay, so down here got 1, 2, 3, 4, 5, 6. Now we're going to change it to 3. So we change it to 3. Okay, and then you push it to the center. So now the structure looks like this now. Okay. Okay. Now the structure looks like this. If you use if you apply case 1 where steel as the reference material. So the structure on the left hand side. Okay. So all these are all your set. Now on your right hand side, everything now is in steel. Because you just said reference material is in steel. Right? So when you reduce your cross-sectional area, right, it's as good for the steel, it's as good as brass with the expanded what? Expanded width. Okay? Does that make sense to you now? So the material resistance to the force is still the same. Okay? Now, someone just say, why do we do this? Okay, why do we do this? We do this because this formula that I circled, the original formula, which is stress X is equal to my over Iyy multiplied by Z. It is only capable of handling non-composite material. Okay, We put a coefficient in front so that it will handle what? Composite material. So how does it actually do it? It is reducing the what? It's reducing the width. What you realize, right? The height did not change, right? The height did not change. Okay. Only the width changes. Right? You can see that now. Okay. And then when we do case number, so I'll do another case. I'll do another case. Okay. So case number 2. Now we use brass as the what? Reference material. Okay, we use brass as the reference material. So now I want you to compare. Okay, so now N of steel now is equal to E of brass. Sorry, E of steel divided by E of brass. Okay, so this is what? 2/1, right? Because this is 200, this is 100. Then when we go for E of brass, or N of brass, so this is E of brass divided by E of brass. Okay, E of brass. This is still equal to what? Equal to 1. Okay, so geometrically, how does it look like? Okay, so the brass did not change, so this is still 6/3. So it did not change. Okay, so 2, 4, 6/3 is still the same. Okay, so this is still your brass. Now the top bit is what? Now you change the steel to become brass. So to enable it to have the same bending resistance, right? We increase the width. Only the width changes. The height did not change. So now the whole thing is what? Whole thing is brass. Okay. Okay. I'm not going to do the example. I'll wait for the example for next week. Okay. If I do now, I'll need another 20 minutes. I believe you guys are exhausted hearing my voice for almost 2.5 hours. Okay. So this is for sandwich material. Now, this week's quiz, this coming week quiz, there will be no sandwich material, and sandwich material I will not put on your homework. Okay, I'm not set your homework yet. Okay, give me to about 3 o'clock. I'll post your homework. Okay, and that's all for the lecture. Don't go yet. I don't want you all to go yet. Okay, you all hold on a bit. I need to ask you a question.